We're recording. Okay. So, look, I finished grading the test. So, I mean, all of the comments on the exam are in Canvas. Okay. So I did all of that, I typed all that into Speed Grader. Okay. So you should be able to see with fair clarity what's going on in there. The one that kind of disappointed me fair amount was one of the true false questions, namely the meaning of like a triple integral over a solid. Okay. Clearly that can't just be the volume of that solid unless the function that you're integrating is 1. Yes. Okay. But I kind of made a big deal at various points about the fact that the triple integral of a function over a solid, right? So it's a function of 3 variables, whose graph lives in 4-dimensional space. You no longer have any kind of geometric meaning to what's happening there. Okay. Some of you, paid homage to like some kind of 4-dimensional volume or something, hypervolume. Fine. Okay. I gave you credit for that. But in general, what I said is you could think of it as some kind of scaled average value. Yes. Okay. In some sense, that integral, in fact, it is just the average value of the function over the solid times the integral of that solid, the integral over that solid of 1, which really is the volume of that solid. Okay. So it's the average value scaled by the volume of that solid. Okay. So that was the one that was a little bit disappointing. The other stuff seemed to go decently well. So that was good. So I have to look on the bright side of life, as is often the case. Okay. Give me until Wednesday to kind of decide precisely what we're going to do about the final. I'm still sort of debating in my own mind what's happening there. But in the meantime, there are things for you to work on. I put up a couple of short web assignments. I think one of them is maybe due sometime. And the other one is due some other time, like on Friday or something like that. So, yeah, take a look at those, make sure that you understand what's going on, and it'll all be good. I'm not going to assign any homework for the last 2 sections, but we'll do plenty of problems in preparation for the sorts of things you might have to do. The last 2 sections of chapter 15 are not merely, it's actually fairly important. It's basically like trying to find something like Green's theorem. Remember, Green's theorem applied to curve integrals or line integrals, if you will, that happen to begin and end at the same place. Yes, that's what Green's theorem dealt with. But we're going to look like something for Green's theorem in relationship to surface integrals. Okay, surface integrals, which we're going to talk about now with gusto. Okay, so let's do that. So first of all, this is the stuff from section 15.6. Okay, so this is section 15.6. It's on surface integrals. Surface integrals. And I started kind of introducing what we're going to be looking at last time. Now, the surface area of S, okay, so by the way, I mean, I'm just going to go ahead and erase this. And for simplicity, we'll write things like the area of a surface S is given by this. And incidentally, here, we're actually thinking of the surface S as being parametrized by R of UV, which, by the way, is, as you know, like X of UV, Y of UV, Y of UV, and Z of UV. So X, Y, and Z all depend on U and V, okay? And when we have had to in the past, things like surface area, what we've done is we've computed the U derivative of R and the V derivative of R. We've computed the cross product, which gave us a small piece of, well, actually, that just gave us the area of a parallelogram. We shortened that up, though, so that it was an accurate piece of area on the surface by multiplying by dU and dV. Remember that? So we came up with this formula right here. And what I was hinting at last time is, what if we happen to insert a little function right here? Okay, so what if I put like a function f of x, y, z. And I thought of it over this particular surface. Incidentally, sometimes notationally, we don't just write, you know, r of uv. Sometimes we'll actually replace this with just s. Okay, we'll just say, look, just double integrate over the surface, okay? Let's not horse around here. Let's just actually double integrate over the surface S itself, okay? Fully understanding that there's some kind of region that U and V will kind of move around in to help us do that, okay? But we were talking about at the end of last time, what if we were to insert a function right there? Well, then we would have something that should remind us of like the mass integrals we were doing for our line integrals. Yes, remember sort of the mass of the curve integrals that we were doing before. Okay, so let's kind of take a look at that. Okay, so mass integrals. Okay, so how's that going to work? Well, in the case of curves, okay, so if we were doing curves, what sort of situation would we have had? Well, C, we would have had a curve C, which would have been parametrized by like R of t equal to x of t, y of t. In fact, just, you know what, I'm not going to write all that junk out. Okay, so R of t, you know that R of t depends on x, y, and z, which in turn all depend on t. Yes? Okay. And let's see here. So this is for a equal to or less than t equal to or less than b. Okay. And what we did is we had something that looked like this. It was the integral over c f of x, y, z, d little s, where d little s was a small piece of what? What was d little s? What was that? Yeah, it was a small piece of arc length of the curve. Yes? Okay, so this was a small piece of arc length. Okay, that was a small piece of arc length. And then practically speaking, to actually go and compute this thing, what we did is we went integral from a to b, f of, okay, I want to write it this way, like x is going to be replaced by x of t, y by y of t, z by z of t. But a short way to write that is just f of r of t, okay? And ds, what was ds? Do you remember? It was like the square root of, what was ds? It was the square root of what?
X prime of t plus y prime of t plus z prime of t dt.
Well, it was x prime of t squared plus y prime of t squared. Okay, all of this under the square root plus z prime of t squared, and this was all dt. Here's kind of a shorthand way of writing this. It's like the integral from a to b, f, okay, x and y and z all get replaced by what they are in terms of t. So this is f of r of t. And don't you see that thing right there, that square root that we have sitting right there? That's just the length of the derivative of r, yes? Isn't it? If I took the derivative of r, I would have x prime, y prime, z prime. And if I computed the length of that, I would get that thing right there, that gnarly looking square root right there. So this is times the length of r prime of t dt. Okay? So that's what we do in the case of curves. That is like the mass integral in terms of curves. And we know full well that what's really going on here is a direct extension of all the integral stuff that we did in Calc 2, yes? Or Calc 1 even, really. Like where the curve is no longer just an interval on the x-axis. The curve could be anything in three-dimensional space, yes? And the actual answer that we get here is going to be kind of the area under f of x, y, z as it goes above and below the curve, okay? Where if I go below the curve, that area is counted as negative. Above the curve, it's counted as positive. Well, for surfaces, it works pretty similarly, okay? So let's just, let me kind of write down what happens for surfaces, okay? What about for surfaces? Well, here I have S, and S is going to be parametrized by R of UV, and you know full well that means that X, Y, and Z all depend on the parameters U and V, okay? And let's just say, here it's a little bit more complicated. I'll just say that U and V belong to R, okay? The region might not just be like a couple of intervals for U and V. It might be something complicated like a disk or an ellipse or something like that, yes? But U and V are moving around in this guy, this region R, okay? And the double integral over S of f of x, y, z, d capital S, what we were talking about above is this d capital S. You think of this as a small piece of what? Small piece of what? Surface area. Of surface area, okay? ds is a small piece of surface area. So practically speaking, how, pray tell, do we actually compute this thing? Well, it's going to be the double integral over the region R. That's where U and V live, yes? I'm going to plug in for X what X is in terms of U and V. I'm going to plug in for Y what Y is in terms of U and V. I'm going to plug in for Z what Z is in terms of U and V. So this would be F of R of UV. That's kind of a shorthand way to do that. And I want to take that value and weight it by a small piece of surface area. But didn't we already figure out how to do that? Yeah? That was just the length of what? The length of RU cross RV. And then we say du, dv, or dv, du, whichever happens to be convenient for us. Okay? Don't you see the parallel between these two things right here? Okay, this and this. Look at that. Doesn't that look almost exactly the same? Yeah? Except we've exchanged a curve for a surface itself. Okay? And just like the curve situation, we were thinking of, okay, how much time does this function spend above and below the curve? In this situation right here, what am I thinking? What am I kind of figuring out? Well, I'm figuring out how much time this function spends above and below the surface itself. Yes? So basically what you're going to get is the volume between the surface and the function. Okay, it's going to be the volume between the surface and the function, where if I happen to be above the surface, that volume will be counted how? Positive. And if I happen to be below the surface, if F happens to dip below the surface, I'm going to count that volume as negative. So what we've done is we've kind of given ourselves the ability to not be tied to regions that live in the XY plane anymore. Don't you see? Now I can actually have it like some arbitrary surface in three-dimensional space. And I can kind of think about the volume underneath the function f of x, y, z, where the volume above the surface is counted as positive and below the surface is counted as negative. Yes? And so it's a direct extension of what we've been doing, or what we were doing in chapter 14, for sure. Okay? Okay, any questions on that? Okay, so those are mass, that's the kind of analog of a mass integral for a surface. It looks very similar to what we did for curve integrals in that case, except that we've gone from just one parameter to two parameters. Okay, any questions on that? We're going to do an example, but are there any questions? Okay, before we do an example, let me just say, we had two kinds of curve integrals. We had mass integrals, and what were the other kind of curve integrals that we had? Work, yeah? Here we have a mass integral for a surface. We're also going to have a work integral for a surface, but it's going to be a little bit harder to define what we mean by work if I'm dealing with a surface itself. Yes? Okay. We're going to have a very clear idea of what side of the surface we're actually on. And it's probably not clear to you right now why that would be the case. But when we were traveling along a curve, there was a clear direction that we were going in. Yes? And that direction dictated how much work was being done by the force field on us as we moved. When I'm on a surface, I'm just flowing around, right? I don't have to go one direction or the other, yeah? But so I have to have some kind of clear idea of what I mean by direction when it comes to an actual surface before I can define a so-called work integral in that particular case, okay? But let's do an example of the mass variety here first, okay? So example, let's look at this. So, okay, example. So let's compute the double integral over S, f of x, y, z, d capital S, where f of x, y, z is just something kind of easy. It's just going to be x, y, okay? And S is the surface parametrized this way. S is R, and you're going to get lots of practice with these sorts of things on your web assignment, but it's going to be the x coordinate is 2 cosine of u, the y coordinate is 2 sine of u, and the z coordinate is v, okay? And this is for 0 equal to or less than u equal to or less than pi over 2, and v goes between 0 and 1, all right? Okay. First of all, what is that surface? What is that surface? What is it? Well, look, the easiest way to figure that out, I mean, you could go actually graph this thing in GeoGebra. That is a possibility, but I want you to have good sort of non-technological intuition about these things at first, okay? If you look at the x and the y coordinates, 2 cosine u, 2 sine of u, excuse me, what's that? That's a circle of radius 2, centered at the origin. So that's what's going on with x and y. But how much of the circle is it? It's just right. It's like, okay, it's a quarter circle. Yes, it's the quarter circle. Okay, so this is a quarter circle. Okay, and then this guy right here, I mean, seriously, this part right here is pretty easy. All that does is it kind of stretches that thing out, like the z coordinate just is free to move between 0 and 1. That's what that's saying. Yes, the z coordinate is free to move between 0 and 1. So like we could actually plot this thing by hand. Okay, in fact, let's do that before we get going here. Okay, so let's see here. There's x, y, and z. I'm talking about this quarter circle that happens to live in the talking about this quarter circle of radius 2. Okay, this is of radius 2 that happens to live in the first quadrant right here, centered at the origin. Yes, and then z is allowed to move freely between 0 and 1. Okay, so here we go. This is what we're looking at right here. Look, that's our surface. Okay, so that is S. Okay, isn't that cool? Yeah, so we have S, looks like this. Okay, now you might say to yourself, look, that thing is like a vertical surface of some kind. What in the world are you talking about? You talk about volume of it and whatnot. Well, that's why it's kind of nice to have this thing of this idea of mass in our minds, where F is actually the density at any given point or whatever. Yes, and then we just kind of weight that by a little piece of surface area at every single point. Okay, so how do we compute this thing? Well, okay, it's going to be the double integral. All right, so first of all, let's not get ahead of ourselves. What's like r sub u? Okay, well, r sub u, that's going to be -2 sine of u, 2 cosine of u. Okay, 0. Of course, the u derivative of v is just 0. And r sub v is equal to, all right, r sub v. Oh, how nice. What happens to the first two coordinates? What happens to the first two coordinates? I get 0 for crying out loud. Yeah. 0, 0. Okay. And then what's the last coordinate? 1. Okay. Okay, how interesting. Okay, so what is RU crossed with RV? Okay, RU crossed with RV equals, okay, let's figure this out. If I cross out the first entries here, it's going to be 2 cosine u times 1, and the zeros just go away. So it's going to be 2 cosine of u. Okay. And when I do the second coordinate, I do it kind of backwards. I cross out the second coordinate. I go 0 times 0 minus negative 2 sine u times 1. Minus negative is positive, so that's 2 sine u. And then 0. Of course, I forgot my commas up here, but I think you knew what I meant. Okay. So there's RU cross RV, right? Now I need the length of RU cross RV in order to get that sort of small piece of surface area that we so desperately need. Okay, RU cross RV. Okay, what's that? So think about it. Like, what am I going to get? It's going to be the first coordinate squared plus the second coordinate squared plus the third coordinate squared, square root. But I have a cosine and a sine in there. Yes. What am I going to get when I do that? 2. Okay. 2. Okay. And so here's the thing. This, right? So this junk right here, the range of u and v, that is what determines our region R over which we actually integrate. Okay. So let's write some stuff down here. Okay. So let's see. F of x, y, z. So this is going to be f of, okay, whatever x is, I replace it with what it equals in terms of u and v. So x is going to be 2 cosine of u. Y is going to be 2 sine of u. And z is going to be v. And then I have to multiply this by the length of RU cross RV du dv. Or dv du, whichever, however you want to roll with this. Okay, and I'm double integrating over R. Well, let's just straight plug what everything is in here, okay? F of x, y, z is just the function x, y. So I'm going to go 2 cosine u times 2 sine of u. That's what x and y are, okay? So it's going to be 2 cosine of u times 2 sine of u times the length of RU cross RV, which we have just determined is 2 all the time. U dv, right? So it's 2 irrespective of wherever u and v happen to be. Okay. Now I put du dv. Fortunately, the region in this case is quite easy for us to deal with. So what is the range for v? What do I put for v? 0 to 1. And what do I put for u? Well, 0 to pi over 2. And now we're in business, right? So let's see here. Maybe I want to save, maybe I want to save a factor of 2. I'll pull out the 4 right here. Okay, it's going to be the integral from 0 to 1. By the way, what can I do with the, I mean, I don't want to be too tricky here, but look, are there any v's at all in any of that stuff on the inside? No. So really I can kind of get rid of that thing immediately. Don't you see? Okay, I can actually get rid of that junk immediately. Okay. And all I have left is just the integral from 0 to pi over 2 of the u stuff. Right? The v integral is just an integral from 0 to 1. So that's just like multiplying by 1. If it would have been from 0 to 5, I would have multiplied by 5. Right? That's just fundamental at this point. Okay. I'm going to pull out the 4 though. I'm going to say that this is the integral from 0 to pi over 2. And I'm going to write this as 2 sine u cosine u du. Why did I save the 2?
There's a trig sub you can use.
Well, yeah, there is. Okay, so like what, okay, or I could, right, I could have done a substitution. I better not say u substitution in this case because I'm already using the variable u, yes? There's a substitution that can be made, but I could also, it's kind of nice to remember some past cobwebbish encrusted trig identities. 2 sine u cosine u, what is that? Remember the double angle formula? Is that not the same thing as sine of 2u? Do you remember that? Okay. This is 4 integral from 0 to pi over 2 sine of 2u du. Okay, and what's the antiderivative of sine of 2u? Yeah.
Wait, I've got a question.
Yep.
Can you not just integrate it and make it sine squared u?
Right. You could have done that. If you would have used like a W substitution of some kind.
Yeah.
Yes, because the derivative of sine is cosine. Yes. Okay. Right. Okay. So like here, let's do that actually, since that's the thing that was actually suggested to me. So you're saying to go ahead and use what? W equal to what?
Sine of u.
Yeah. So if I put W equal to sine of u, then dW is equal to cosine of u du. Yes. And so I can just straight up pull out the 2, okay, which is 8, the integral, okay. Sine of 0 is 0, sine of pi over 2 is 1. And what's left behind here? What am I going to have? What's my integral going to be now? That's just W dW. Yeah, I mean, how easy. Okay, so it's going to be 1/2 W squared. Okay, so it's going to be 8 times 1/2 W squared integrated between 0 and 1. And we get 4. Okay, 4. So 4 is the result of that surface integral in this particular case. Okay, does that make sense? Okay, it's fairly straightforward. It's just a kind of a small extension of what we were doing in the case of surface area computations, and it's a direct extension of this junk that we were doing up here for sure. Okay, it's a direct extension of a curve integral where we were kind of thinking about mass over that curve. Okay, exactly an extension of that. Any questions on that at all? Okay, I trust that makes sense. Okay, now, so what's the big question that should be on our minds at this point? Okay, what about, should be this should be the question on your mind. What about an extension of work integrals? What about that? We had work integrals in the case of curves. Yes. Okay, so let's kind of let's work on that for a minute. All right. So let's see. So work integrals. Okay. So in the case of a curve, what we did, okay, so here's our curve, which is parametrized by R of t for A equal to or less than T equal to or less than B, okay? And we also had a vector field F, and let's just go ahead and just imagine that F depends on X, Y, and Z, okay? And let's, let's put M, N, and P. And here is the 3 coordinate functions. All M, N, and P, all of them depend on X, Y, and Z, by the way. Yes? M, N, and P, the coordinate functions depend on X, Y, and Z. Okay? Then we had this. It was like the integral over C of F dotted with dr. Okay? which by the way, an alternative notation for that was just m dx plus n dy plus p dz, okay? Right, this is how we defined our work integrals, okay? Basically, what we wanted to do was take the dot product with f at a given point and the direction that we were moving in so that we could figure out how much work was done in moving the particle along. But we wanted to sort of shorten the derivative enough so that because you don't actually move the particle all the way along its derivative vector. Yes, that's not what happens. So we shortened that with dt. Don't you remember? Yeah. So we had f itself dotted with r prime of t dt. So practically speaking, the way that we computed this was, you know, the integral from a to b, f, okay, we plugged in what r of t was in here. And this was dotted with, this is a dot product, so I'm putting a giant dot, yes, dotted with r prime of t dt. That is how we did this. Yeah? That's how we did this. All right. So we're going to do a similar thing here for surfaces, okay? But we have to make sense of what it is we're actually doing and why it's useful. Okay, for surfaces, we have this notion not of work, but we're going to have a notion of flux. Okay? Flux across the surface itself. So once again, we're going to have a parametrized surface. We're going to have a vector field that we're thinking of as acting on that surface in some way. But we want to measure how much strain that force field is actually putting on the surface itself in a particular direction. Okay? That's flux across a surface, yes? This is a notion that will come up time and time and time again in like physics and electricity and magnetism applications. Okay, flux across a surface is actually a fairly important concept. So let's start with a surface. Okay, the surface this time is going to be parametrized by two parameters. Okay, for u and v in some region R. Okay. Again, we have a vector field f of x, y, z, which in theory could act at any point on this surface. Okay. So I have this vector field f of x, y, z. And now we're kind of in a pickle, okay? If you have a surface, before we had a curve, right? It was clear that we were kind of like moving in one direction, correct? Okay, I had some kind of curve in three-dimensional space over here, okay? You know, that was kind of going along like this. And if you were talking about kind of being at any particular point on that curve, you know, if I was moving in this direction, then it was clear, you know, I had a tangent vector right here at this particular point. And we could look at sort of the force field and that thing that dotted together, yes? But for a surface, things are a little bit more messed up. I'm not like moving in any particular direction. I have complete freedom to move around on the surface, okay? So what in the world do I measure? It's not going to be exactly like work, because if I'm moving around on a surface, I'm not just trying to go from one point to another like I was along a curve. Don't you see? Okay. If I had a curve, it was clear that I was trying to move from some beginning point to some ending point. If I'm on a surface, I'm just moving around on the surface. I'm not trying to go from one point to the other necessarily. Yeah. So it's not going to necessarily be like work in the same sense that it was for curve integrals. Okay, so let's actually look at a picture of a surface here. So here's our surface S. Okay. Here's our surface S right here. Okay, so this is S. Okay. And I don't know, suppose I'm at this point on S or something like that. Then I don't have any kind of clear direction from that point. I don't have to go one direction or the other. Yeah. So what we do is we actually create a tangent, or actually a normal vector at this point. Okay, because a tangent vector isn't going to be very well defined either, is it? Because how many directions could I take a tangent vector in at that point? Infinite, yes. I could go in any direction at all. So what you do instead is you create this kind of what's called an upward oriented normal. Okay, so this is a so-called upward oriented normal. Okay, it's a perpendicular vector to the surface at that particular point. Okay, and just to make sure that this thing, okay, I'm going to put a capital N on this, okay, with an arrow over the top, just to make sure that this thing is kind of like the same height everywhere and isn't necessarily like really long in some places and really short in other places. We're going to make sure that our vector N always has length 1, okay, so that there's no kind of weird distortion happening here, okay? And what we're going to do is to measure strain in the direction of the surface. Actually, that normal vector is pointing kind of in the direction of the surface itself. Don't you see? Yeah. That normal vector is kind of pointing in the direction of the surface. It's perpendicular to the surface itself. And what we're going to want to do is measure the amount of fluid flow in the direction of that normal. And that in some sense measures kind of strain put on the surface at that particular point. Okay. So what we're going to do for the surface integral in this case is we are going to take the double integral. So here's the notation. It's the double integral over the entire surface. And you're going to take F, and at every point, you're going to dot it with this normal vector. The normal vector depends on where you are. And then you're going to take a tiny piece of surface area in doing that, okay? You're going to say, well, that's the amount of strain at that particular point on the surface itself, okay? It's pretty similar to the sort of thing that we were doing over in the case of curves, except in this case, we didn't have a clear direction in terms of where we were going. But we can at least talk about a side of the surface itself. So I'm looking at this kind of top side of the surface. This guy right here is called the upward oriented normal, okay? And in some sense, this kind of tells us the sides of the surface. We need to know, okay, which side of the surface am I actually on? When they ask you for the upward oriented normal, they mean that the Z coordinate needs to be positive, yes? Upward oriented means that the Z coordinate of that normal needs to be positive, okay? Well, practically speaking, how do we actually find this integral? How do we actually find this integral? Well, first of all, we need to figure out how to find this normal vector. We need to figure out how to find this normal. What do you think? How do you find that normal? What would we do? We want it to have length 1. Yeah.
Wouldn't we need to take the gradient of the 4-dimensional function and use that as a level surface?
You could do that, yes. That would be one way to pull it off, yes. But I've actually got this thing parametrized already. So what could I do to actually, I mean, you're absolutely right. We've done that sort of thing in the past where we've said, oh, I want like a perpendicular vector. We did that to find tangent planes. Do you remember that? Yeah. But here I've got this thing parametrized, R of UV. How could I figure out what N is? Look, isn't R sub, I mean, think about this for a second, okay? So like, I don't know, maybe this is R sub U. Maybe this is R sub U. Maybe this is, well, actually, I'm gonna, just so that my picture isn't messed up, okay? Maybe this guy right here is R sub V, and this guy right here is R sub U, okay? And those are kind of tangent at that surface. And if I take the cross product of RU and RV, I'm going to get a perpendicular to the surface, yes? Okay. So N, let me just kind of write this down. N is going to be RU cross RV. And notice I kind of wrote this raised up a little bit for a good reason, because what did I say I wanted to be true about the normal? Just to make sure we don't get a distorted perspective about the amount of strain across that surface.
Length is always 1.
Length's always 1, which means what do I have to divide by, for crying out loud?
That gets you.
Yeah, I have to right? The magnitude of RU cross RV. Okay. Yeah. So that's helpful. I have Rn. Okay. I take RU cross RV. I take the length of this thing. Okay. And by the way, you need to make sure that the Z coordinate is positive. If you want the upward oriented normal, sometimes they'll say the upward oriented normal. And in that, if they say that, they want you to have the Z coordinate be positive. So you need to make sure that that's true with your normal vector here. So now that gives us a way to practically compute this thing. Okay, so watch this. So this is equal to the double integral over R. I'm going to replace X, Y, and Z in the vector field with the X, Y, and Z coordinates in our parametrized surface. So this is going to be R of UV dotted with our normal vector, which is RU cross RV divided by the length of RU cross RV. Okay, but here's the thing. Remember, we also had this small piece of surface area over which that was supposed to be happening. Yes? Yeah? We had this small piece of surface area. And what is that small piece of surface area? How do we compute that? Do you remember? It was the length of RU cross RV, the UDV. Yes? So do you see what's going to happen here? Okay, so it's going to be the length of RU cross RV, du dv. What's going to happen to the lengths of RU cross RV? What's going to happen to those things? They cancel, yeah? And so what we end up with here is the double integral over R, vector at any point on this surface, dotted with RU cross RV. Okay, that is a vector, du dv. Okay, this right here is what we refer to as the flux of F, the vector field, across the surface S. Okay, so that's the flux of F across S. And we have a well-defined side for the surface. By the way, that's not always possible to do. That's kind of an amazing thing. There are weird surfaces that really don't have well-defined sides. You ever seen something called a Mobius band? If you run your finger along a Mobius band, you're gonna realize that it has a single side and that's it, okay? In three-dimensional space. Same thing with something called the Klein bottle. I don't know if you've ever seen one of those before, but it's sort of interesting. Here we have to have surfaces that have well-defined sides. There's going to be one side and another side so that I can always guarantee that I can get a positive Z coordinate. Yeah.
When you say side, what exactly do you mean?
Well, that means that like I can actually flip. I can actually, that means that there's like a boundary that I can see right here. And there's a boundary between, so let me just kind of highlight this in yellow. You see this guy right here?
Mm-hmm.
This is something that would never appear on something like the Mobius strip, for instance. Okay, so sides mean that there's a well-defined boundary where the kind of normal vector, this perpendicular vector, will suddenly like flip over once I kind of go across that boundary. Yes?
So like a non-differentiable point.
Yes, in some sense, yes. But it's important that we kind of be able to refer to that boundary. Yeah.
So if you had like a full sphere and not just a hemisphere, would that not have one side?
Well, there they would say like the outward, I mean, yes, that would be okay as well. There you have like an inside and an outside. As long as you have an inside or an outside, you have well-defined sides. As long as you have a top side and a bottom side, you have well-defined sides. And top side is going to be defined by like, oh, the normal has Z coordinate that's positive versus negative or something. If you have a Mobius strip, you're not going to be able to say that clearly, yeah? Because as you move around, if you move your normal vector around, eventually, if you keep moving around it, you're going to be flipped over on the other side. Here, if I move this normal vector around, and I don't cross over that yellow boundary, it always kind of stays where it should, yes? But if I take that thing and I move it around the Mobius band, it will flip over eventually. There are weird surfaces that actually do that. We don't want those weird surfaces. Those are just weird. They actually, a lot of them actually live in higher dimensional space, and we're trying to like look at them in 3-dimensional space, okay? That's the problem. But this one clearly has sort of like a top side and a bottom side that we could deal with here, yeah? Okay. All right, other questions on that? Other questions?
Yeah, where exactly does the term flux come from?
Well, flux actually means flow. Flux is, I think, I mean, look, I might be wrong about this, but I think it is Latin for flow. Okay, so it's like flow across the surface. So you're measuring the amount of flow across the surface itself. If you think about the surface as kind of like a semi-permeable membrane where the flow is kind of going through it, you're measuring the amount of fluid that's like going across the surface in the direction perpendicular to the surface. So in some sense, it's measuring strain put on the surface. Yes? Okay. Yeah.
Isn't a Mobius strip how time travel works?
Well, according to Tony Stark, but I know where that's coming from, but yeah, he put a Mobius strip in there and solved time travel. I doubt it would be that easy. Okay, unfortunately. But a Mobius strip, it really is to sort of fully understand what's going on. It really does kind of live in higher dimensional space. Okay, so. All right. So we have mass integrals and we have work in quotes integrals, but it's not really work anymore. It's flux or flow across the surface. So we're going to be computing flux integrals next time. And it will be our goal to find things that help us compute flux integrals more easily, because flux integrals are a nightmare most of the time, okay? You will see it. Most of the time, if you try to compute a flux integral from scratch, it will be like entering the 7th circle of hell, okay? So most flux integrals, you're going to want to have something that kind of helps you out, yeah? All right.
I don't think I want a calculator.
I'll leave it at that. We will try to do a couple of flux integrals, but then we'll find some other tools to do it as well.